Okay, so hi everybody. Today we're very happy to have Roberto Emparan from Barcelona, who will tell us about quantum cross-section of near-extremal black holes. Please, Roberto.
Thank you, Sahas, and thank you for the invitation to talk here in this seminar and this audience where I have we're talking many friends and people that I have lots of scientific contact over the years. So it's my pleasure to be here talking with you. So I'm going to talk about this. I mean, the title is this quantum cross-section of near-extremal black holes. I will try to explain what I mean by this, but I think I like to motivate this. See how it works. Yeah. The main motivation for this is something that I think it's a very basic question in quantum gravity, whether we can observe somehow and safely, I mean, large quantum fluctuations of the space-time geometry. By safely, I mean that we don't have to jump inside a black hole and die while we're measuring these large quantum fluctuations. Okay, so we want to do them safely from a distance and large quantum fluctuations that may be controllable. I think this is one of the main points or a very important question in quantum gravity. So how can we do this? As I say, can we actually have control over quantum fluctuations of the geometry in some setting? One of the important things, one of the important developments in recent years is the full realization. There had been hints maybe before, but now we understand this much better, that when you have black holes which are close to extremality, close enough to extremality, and I'll be more precise about this, then these black holes undergo large but still controllable quantum fluctuations. The essence of the idea is that these black holes have very long throats, and then the length of the throat, we've learned that this is a quantum variable that has large quantum variance. It's not something that's it's not a narrow semiclassical calculation with small fluctuations. This length of the throat has large variance. And this happens while the curvature still remains small. So it's not that we're going to regions of large quantum fluctuations because, well, space-time is becoming singular and everything goes out of control. Here, the curvature remains small. So it allows us to remain within a regime where we can do reliable calculations. So one thing that's been learned, and the main paper over here, building on previous work on things like the gravity. So there was a paper by Luca Elias and Joaquin Turiazi, who studied the thermodynamics of black holes close to extremality, black holes not near BPS, but near extremal. And one of the things that they found that these large quantum fluctuations, when you compute them, and I will go in more detail over how this is done, this large quantum fluctuations, one of the effects that they have is that they reduce drastically the density of states. So if you consider the density of states...
We can ask questions as we go along, right?
Yeah, that's fine, yes. I don't have any time limit, so I mean, we can go on for as long as you want, yeah.
That's a separate question to the organizer.
I do have a time limit, but it's, I mean, not, yeah.
Thank you. So you said near extremality, but now not near BPS. By that you mean these are rotating black holes rather than charged black holes?
Or they could be charged black holes, but in an embedding or where you don't have supersymmetry. For instance, your theory is just Einstein-Maxwell without fermions. And then there are also embeddings of within, say, n equals 2 supergravity. You can have the Rayleigh-Nostrom black hole. It admits an embedding which is supersymmetric, but also another one which is not supersymmetric. For instance, I mean, since you know about D-branes and all of these things, you can have the Rayleigh-Nostrom black hole realized as a D0, D6 bound state.
Mm-hmm.
And D0, D6 is not supersymmetric.
But there is a bound state.
There's a bound state, yes.
Okay.
And there are other ways of embedding it, but I mean, even in supergravity, without talking about the D-branes, you can have the Rayleigh-Nostrom black hole embedded in a supergravity theory in such a way that there are no clean spins.
Yes, I understand.
Yeah.
Thanks.
So that's the context. I'm not going to say anything about supersymmetry, at least not during the talk. If you want to, I mean, I can say things kind of after the talk or near the end of the talk. Okay. So there are these near-extremal black holes. What do I mean by this? So the density of states of a black hole, according to Bekenstein and Hawking, when the black hole is large and semiclassical, and then it's given by the exponential of the entropy. But what's been found is that as you go closer to extremality, and this E is the excitation energy above extremality, this is the extremal mass, this is the total mass, so this is energy above extremality. When you reach a scale, the scale is parametric of this order, something that's small in the entropy. When the black hole is very large, this scale is very small. This is the extremal black, or the naive extremal black hole entropy. Then these quantum effects can become very large, and the density of states, instead of going to a finite value at exact extremality, the density of states goes down, decreases. We don't have full control over this region, but we certainly can see that the density of states is approaching a value that's much smaller than the Bekenstein-Hawking entropy. Okay? So that was one of the puzzles, for instance, why these extremal non-supersymmetric states did have all of this entropy. That's something that's not generic. Well, this is now understood much better. The entropy of these extremal ground states, it actually goes to a number that's order 1 and not order 1 over G, or order 1 over G. So that's one effect that was found in this paper. Later, people have also examined other consequences. This means that, the black holes close to extremality are very different than semiclassical physics would tell you.
Roberto,
Yes.
just a question. This argument about the density of states is done through the Schwarzian theory?
Yes,
okay.
Exactly. So all of this is dominated by the quantum Schwarzian. The Schwarzian allows you, the classical Schwarzian also allows you to recover this, but here the Schwarzian is strongly coupled, and that's where quantum fluctuations become important.
Okay.
So the black hole in this regime is a fully quantum object. And one of the consequences also is that Hawking emission, for instance, is suppressed. Why would you expect it to be suppressed? Well, you have fewer states available for radiating. So you might expect that the black hole emission is also going to be suppressed because the black hole has fewer states, and then there is the rate of emission, you expect that it's suppressed. And this has been computed more recently. This was a paper last November, I think it was last November, where they computed, taking into account these quantum effects, they computed the full quantum answer, and then you see that the Hawking emission is strongly suppressed relative to the semiclassical calculation. This is for an energy. There's this scale that will be mentioned repeatedly. It's going to play a role. It's EB. B is for breakdown. It's something that I will mention why this B is there. But it's the scale. This is the energy scale above extremality at which quantum effects become important. So when the energy of the black hole is, say, 1/10 above extremality, 1/10 of this energy above extremality, you see that the emission is much smaller. Largely because, well, there are many fewer states, black hole states, that can emit radiation. Now, the question that I want to address in this talk, the one that I addressed in a paper that I wrote a couple of months ago, is, well, can we probe this object? Imagine that, this is thought experiments. Let's not talk about astrophysical black holes. I can mention numbers for astrophysical black holes. These are thought experiments. We can have a large quantum object, and then I want to know how can we probe with thought experiments that this object that we have there is a quantum black hole. So one could try to do this, well, through Hawking radiation. So first of all, you want to create this object. Okay, you want to create this large near-extremal black hole. How can you do it? Well, imagine that you have resources at your will that allow you to create a charged black hole. Typically, it will be away from extremality, but then you let it evaporate. If the black hole is large enough, then evaporation proceeds mostly through emission of neutral radiation. You can suppress charged particle radiation if the black hole is large enough. So then you let the black hole evaporate until it's close to extremality, and when it's close enough to extremality, then you're hitting this regime of large quantum fluctuations, and then you detect that the radiation that it's emitting deviates away from Hawking's original calculation. Okay? It's essentially probing the graph that I showed earlier to measure what's the emission of quanta as a function of energy above extremality, and then you see that it's different. So that's a way of thought experiment for probing without having to go very close to the black hole. You just observe it, and then you see that it's emitting in a way that's different than Hawking predicted. Well, one problem with this is that this process is really painfully slow, okay? Because essentially the reason is that, well, first of all, you want to form a charged black hole, and then you want it to approach extremality through evaporation. That's going to take ages. I mean, when I mean ages, I mean exponentials of ages, okay? So it's a very slow process to first get to extremality, and then the emission of this quantum. Bear in mind that the temperature is very small, so emission is very suppressed, okay?
This depends on the size of the black holes.
It
This is
depends
true
on the
for
size of
large
the
black holes, but not for small ones.
Yeah, but then the thing is that if you also want the black hole to remain charged, so the black hole is going to lose charge by Schwinger pair production, essentially, because if it has charge, then there's going to be a possibility of creating electron-positron pairs near the horizon, and then this is going to discharge the black hole. Now, this Schwinger pair production of charged particles, that's proportional to the strength of the field outside the horizon. And the field outside the horizon of a black hole, the electric field, is very small if the black hole is very large. Essentially because even if it has a large charge, then, well, I mean, it's Coulomb telling you 1 over r squared, and you have a q over r squared. The radius of the black hole is of the order of q. So the electric field outside the black hole goes like 1 over the charge.
So
And the
it's
charge
telling
like,
us that the black hole has to be large
it has to be large
for this setup, and
exactly.
then it will be very long.
Yeah, then it will decay through mostly emission of neutral particles, neutral radiation. Then if it's smaller, then it will discharge very quickly. Okay, this depends essentially on the one reason that this is such a large value is because the charge to mass ratio of electrons, which are the particles that you would use, then this charge to mass ratio is very large. It's 10 to the 21, okay, for electrons. So the black hole has to be very large. So if you try to plug in any realistic numbers using the standard model matter, then you're going to get numbers which are very, very large for it. So this is going to be very slow. But well, I'm doing, again, thought experiments, and I want to know whether I can do this in a different way. So if you're an experimentalist, maybe it's something that you want to try to do, since the problem was here that the scales were scales that were very large when h bar goes to 0. Can we probe this quantum black hole using classical means? And then we can do two things. First, maybe we want to form the black hole to go close to extremality through classical collapse. Okay? And then we want to observe it classically as well. We are going to scatter a wave and then observe, well, what is the result of this scattering wave. It's like shining a light on the black hole and try to see what this light gives us. Okay. Let me first mention this. It's not the main part of the talk of my work, but I want to mention it because recently it's been proven by mathematicians that you can fine-tune collapse of charged matter. This is similar to critical collapse, where you fine-tune your initial data so that you land on, say, well, in the case of critical Choptic collapse, you can fine-tune so that you form a singularity, Planck mass object. Here, the idea is that you collapse now charged matter, and you can fine-tune it so that the result is forming something that in classical terms would be an extremal black hole, an exactly extremal black hole.
It is not clear because of the same argument that you mentioned before, that this result is correct, because of the discharge issue.
Yeah, the discharge issue is again.
So
yeah.
they in this world they ignore the issue of discharge.
They ignore
if you include the issue of discharge, which is very subtle.
Yes.
And I think I don't have a complete proof.
Yes.
But with Shachar Hod, we have been working on this, and we almost have a proof that that this result is not valid when you include the discharge. And I am definitely there is one issue that I don't have the mathematical proof, but I'm convinced that this result is correct. That and this results in the sense that you will not be able to get a classical extreme black hole because of the discharge.
Yeah, I agree with you. I mean, certainly, I mean, one reason that they don't consider this is these people never consider quantum effects. And the discharge will be quantum per production, and that's something that they are never considering. Everything that they're doing is classical evolution.
Yeah. So, but the moment that you talk about quantum physics, then this result should be forgotten.
I don't think it should be forgotten, because I've been discussing with them, with some of them, also with Michalis Dafermos, who was advisor of some of these people. I think what should be forgotten is the conclusions or the way that they're stating their conclusions, because they say that, well, this means that the third law of black holes is wrong. I think that's nonsense. Essentially, because if you neglect quantum effects, we know that the third law of thermodynamics, in order to make sense of it, you need to take into account quantum effects. It's something about properties of ground states. You cannot neglect quantum physics when your temperature is low enough. And this happens in systems in the lab, and it happens also in black holes. So that's one of my points. So what you're saying is that it's right. So, but I think that if the black hole is large enough, per production or discharge can be suppressed. For any realistic black hole in the universe, this is not going to happen, I think. But yeah, it's true that discharge is something that is going to be a factor here. But even then, I just said that the extremal black hole doesn't exist as a classical object. The reason is essentially, and I will get back to this point, I think it is an important point. The classical extremal black hole, we should treat it as something that it's not a good solution, because quantum fluctuations are large. It's not a good saddle point of our theory. It's not a good semiclassical solution. A semiclassical solution is good when quantum fluctuations are small. In this case, as the temperature goes to zero, quantum fluctuations become arbitrarily large. So it's not a good saddle point of your path integral, if you want, the classical extremal solution. The way that I put it now, I mean, I talked to students and other people, is that studying the classical extremal black hole is something that you can do, but it's as worth doing as studying the classical hydrogen atom. And studying proving theorems about the classical hydrogen atom, you can prove that the ground state of the classical hydrogen atom doesn't exist, and you can go on and prove more and more theorems, but they don't make sense because the classical hydrogen atom is not a thing in our universe, at least close to the ground state. It's the same thing here with the classical extremal black hole. The classical extremal black hole is not a good semiclassical solution in a quantum theory. If you want, it's an artifact of taking the wrong order of limits. If you first take the limit h bar to 0 and then t to 0, then you get it. But if you want to take with finite h bar, you want to take t to 0, then you can never get to the classical extremal black hole because h bar effects are going to be important. Okay. So this object doesn't exist. So how do I interpret what these guys are doing? Instead of saying that the third law of black holes is violated, I think that what they are proving is that you can have classical collapse. And classical collapse is something that happens quickly. It's much faster than evaporation. You can have classical collapse, fine-tuning it, you can land on a black hole in this quantum regime. So using this classical collapse process, you can form a large quantum object, the large quantum black hole. I think that this is a way, of course, you have to fine-tune, which means that you have to hire a group of experimentalists who can do the fine-tuning, but then you can hire this group of experimentalists who are going to set up a cloud of charged dust or charged matter, and then fine-tune it, and then they collapse, and they will form a black hole in this quantum regime. You can't say that you're forming exactly extremal, because that's a classical statement. The quantum statement is that you're forming a quantum near-extremal black hole in a classical time scale. So that's quick, okay? Instead of having to wait several times the lifetime of the universe to let it evaporate to extremality. These are thought experiments all the time. I'm putting this disclaimer at every point, okay? Then, well, we form this black hole close to extremality quickly, and then we want to observe it. So what we want to do is to send a wave to the black hole we're going to measure the absorption cross-section. And that's something that, again, it's something that you can do more quickly than letting it evaporate, collect radiation, plot the radiation, everything. So you send a wave, you measure the absorption cross-section, and then you compare it with the quantum result with the semiclassical result. And this is what I'm going to explain how to do. But so we send a wave to the black hole. How should we do it? Should you send, say, photons that follow geodesics? That's not a good idea. First of all, because these photons may have too much energy or spin that they are going to lift the black hole away from the quantum regime. So in this sense, they are going to destroy the quantum throat. But more importantly, something more important is that if you send something that's probing geodesics, then you're probing not the part of the geometry of the throat that's highly quantum. The quantumness comes from a homogeneous mode, that's kind of an S-wave mode, that from the point of view of the throat looks, it's like a gauge mode, which becomes physical because of boundary conditions. The geodesics are only going to probe the local geometry of the throat. And that's not all of the throat is strongly fluctuation. Not all of the fluctuations of the throat are quantum. I mean, almost all of them are semiclassical. And then these probes are going to probe local geometries, not this overall throat mode that I'm going to discuss later. Okay? So if you shine light rays on the quantum black hole, what you're going to end up with is a classical image. So it's not going to reveal that. So what we need to do is probe the mouth of the throat softly. That means that we're going to use low frequency radiation, and we're also going to do it mostly with S-waves. S-waves are also the ones that dominate at low frequencies, because they are the ones that can more efficiently get close to the mouth of the throat. Okay, so we're going to study low frequency scattering of a scalar field. If you ask about the scalar fields in our universe, well, there's some ultralight scalar out there that we haven't detected yet, but I'm doing the theories game and just putting some scalar field in my game. We can say things about other fields later on. But so this low frequency scattering is dominated by S-wave, which means that it's going to probe the mouth of the throat in a homogeneous way. And then also, since this is going to be very low frequency, then there's going to be a very small perturbation of the throat. So the quantumness of the throat is going to can be preserved. We're doing something very delicate, this quantum state. We're going to probe it softly, delicately. And then we want to measure the absorption cross-section. And for this, we want to compare with the semiclassical result, the one that you get for a semiclassical black hole. And a result that's relatively old, is that when you study S-wave low-frequency scattering of a scalar field of, say, a spherically symmetric black hole, then the universal result is that the absorption cross-section is equal to the area. Essentially because the wave is probing all of the black hole homogeneously. This was, early work on this was done by Unruh in the 70s. The result was proven more generality back in the mid-90s. Now, this result is quite interesting for several reasons. First, because it's simple and universal, but also because you can say, well, the area of the black hole, I know that this is a measure of number of states. So maybe we can take this absorption cross-section as a measure of the number of absorbing states. At least in the semiclassical regime, this is what we would say. Here, we're taking just that this is the entropy, so logarithm of the entropy, exponential, the entropy is the exponential of the entropy is the logarithm of the density of states. So there seems to be this connection between, it's kind of, you can say that it's natural, that if you have a black hole, the more absorbing states that you have, the more the larger the absorption cross-section. So then, if we want now to go, this is what the semiclassical result tells you. If we want now to go to the quantum regime, then, well, I told you at the beginning of the talk that quantum fluctuations make the density of states much smaller than the naive semiclassical result. So maybe you might think, well, then what this will mean is that the absorption cross-section is also going to be much smaller than the semiclassical result, because you have fewer absorbing states, So then it looks like the absorption cross-section should go down when you have this, when a black hole in this quantum regime. Well, what I found when doing the calculations is that this is not what happens. So even if the quantum fluctuations make the number of states much smaller, the quantum result, the actual quantum result for the absorption cross-section is larger than the semiclassical regime. You have an enhanced absorption cross-section, even if you have many fewer states. And in fact, the closer you are to extremality, the larger this discrepancy is. And what's the reason for this? I'm giving you kind of first a summary of the talk, then I will go into the details, okay, on how this is done. So the result, this result follows from two effects. So this is, I have to say, this is, traces also what I was thinking as I was analyzing the problem. Okay, I was doing these calculations last Christmas break. I had the idea from long ago that I could do. In the Christmas break, I had the time to do calculations. I was expecting to find a much smaller cross-section. I did a calculation, I analyzed it a little bit, I did a few plots, and then I found, wow, it's larger. What's going on? And then, of course, what you do is you go and deconstruct the results that you obtain. So the reason that there are the absorption cross-section is larger, even if there are fewer black hole states, is because the quantum effects have two consequences. One of them is that these quantum effects, they enhance absorption transitions between individual states. And that's something, so you have fewer states, but they are more efficient at absorbing radiation. You can more easily have transitions between one state and another state at a different energy. And this is the Fourier transform of something that people have realized also, say, from JT gravity calculations in recent times. That when you study the late time correlations, you consider the two-point correlation function, you introduce some perturbation in your black hole, you study correlations. Correlations initially decay exponentially, like what's normal decay. But then quantum effects, people have, using these JT gravity techniques, seen that the quantum correlations remain larger than an exponential decay. It decays like a power law, and then there are other phenomena. So late-time correlations in a quantum black hole are larger than in the semiclassical black hole. Okay? And then this means that, well, late time means low frequency, which means that, you have larger probability of transitions between individual states at low frequencies. This is the main effect that leads to this conclusion. There's another effect also playing a role, even if it's a secondary role, is that stimulated emission is suppressed. And that's something that you have to take into account together with absorption and stimulated emission occur at the same time, and then this is something that you have to subtract from the total absorption. And then here, the difference is that, well, there's an effect of fewer energy states. If you're absorbing, then you're going to states which are higher energy. If you're emitting, then you're going to states at low energy. And what I'm saying is that at very low energies above extremality, the number of states is more suppressed than at higher energies. So there's an effect, and the fewer states that you have suppress both emission and absorption, but it suppresses more the emission because you're going from higher energy to lower energy when you're emitting. And then there are very few states that you can go to through emission. This is, as I said, this is a secondary effect compared to this one, but it also plays a role. Both effects are at play here. So this is kind of the summary of what I'm going to now tell you a bit more in more detail. If you have questions now, then maybe we can try to address them before I go into more details, into the actual calculations.
Two questions maybe. First, about the universality of the result for the cross-section being the area.
Yes.
I was going to ask whether you have any insight into this universality, but I think maybe you already presented it.
I think
in the way that this entropy, which is responsible for the absorption.
You can say that also at the semiclassical level is simply that, well, you're having a massless wave. I mean, you don't have any complications from coupling or other scales or anything. And it's just probing, S waves are probing the black hole equally from all sides. you would say that a cross section is going to look maybe like a disk. No, in this case, the wave is in the entire sphere. Maybe, yeah. It's a calculation. Well, I mean, you were around also at those times when people were doing these things, so maybe you, yeah. The calculation is simple. Yeah, I think that the main intuition is this one. Yeah. I don't know if you, Barakar, I mean, you're
Sorry,
related.
yes. The fact that it's a universal is not just a calculation. You need to repeat calculation many times for many different black holes, and each time it turns to be this way. So you have to consider some family or something. But I get your answer, and I have a second question.
Yeah, no, actually, you don't have to. You can write down a metric, a generic metric for a spherical symmetric static black hole. So you require that there's a horizon, static and spherical symmetric, and then you're probing. You're sending a scalar probe field into this geometry, and you don't need to consider other black holes. You can do it all at once.
You can show it all at once with some general class of metrics. But it's actually, isn't it also true for non-spherical black holes?
No, in those cases, the calculations are much more complicated. As you can imagine, technically they are more complicated. I don't think that there's any very sophisticated general result.
Okay.
Yeah.
Okay, good. And the other question is about one of your early transparencies with the change in the density of states. Yes, this one. So the dashed curve was the classical result.
Yes.
And then the red curve is the recently found correction.
Yes.
And something here appears objectionable to me, and maybe you can explain to me why it is not. I would expect that if we have any sort of corrections, quantum corrections, they would shift the energy levels, but would not change the overall number. In other words, I would expect that the integral under the curve remains the same. The curve can change, but not the area underneath it. And here it looks like you really lost some states.
Yes. Yeah. So maybe since I will describe this a little bit more, I mean, where this is coming from or how the calculation is done, maybe you can come back with this question later. Okay, so let me get back to where I'm going to. Okay. So yeah, I'm going to now talk about these quantum throats. Well, first, an old-known peculiarity of black holes close to extremality. This was realized in the late 80s, I think it was, by this group of people, that when you go close enough to extremality, something seems to be going wrong. Okay, so the semiclassical, I mean, the black hole, you take the black hole, say, Rasmussen black hole or any black hole close to extremality, you expand it away from extremality in the temperature, and then you find that very generally, the energy above extremality, this is extremal energy, the energy of extremality goes like the temperature squared, with some scale here that's given by the same value that I mentioned before. So what these people realize is that what this means, the fact that this is T squared, means that semiclassical thermodynamics must somehow break down. Because if you're going to emit a single quantum, the energy of the quantum is going to be proportional to T, essentially like T. That's what you expect, the energy of a quantum of Hawking radiation at the temperature T. So the fact that that's linear in T and this is quadratic in T, when T is very small, T squared is much smaller than T. Which means that in this regime, when you have a T less than EB, then this means that if you emit a single quantum of energy, you don't have actually that much energy to emit. Or if you want, the emission of a single quantum is something that's going to have a large effect on the black hole state. It's not going to be just a small fraction of the energy above extremality. It's going to be a large fraction of the energy above extremality. But what this means is that at the very least, semiclassical thermodynamics will not apply, because you have too little energy to emit quanta. So Hawking radiation must change in this regime. Okay, and that was known, say, from many years ago, late 80s. It was something that was known, mentioned once and again, something here and there, and it was never known exactly what to do with it. Essentially, the effect is something that we knew because quantum effects, as I said, you go to the lab, low energy or low temperature lab nearby, and then they will tell you that quantum effects are important at low temperature, and they are crucial. So it's same thing with black holes. That's what we've understood. But black holes, again, it's one of these things that black holes are like other physical systems in so many respects. Okay? So how can one see this? Well, this goes back now to this idea of how you have throats, which are described by this two-dimensional theory of gravity, JT gravity. You know that black holes close to extremality, they develop these long throats. Down the throat, the geometry is you have this factor which is a two-sphere, and then you have this other geometry which is an anti-de Sitter two-space. That's been known for forever. So one thing that you can do then, if you consider low energy, the low energy regime, you can integrate out the sphere. You can do a throat, a Clausius reduction in the throat. Then you obtain a two-dimensional theory, dilaton theory, JT gravity theory in 2 dimensions. And then since two-dimensional JT gravity doesn't have any local degrees of freedom, the only thing that it has is boundary degrees of freedom. The theory of boundary degrees of freedom is a one-dimensional theory whose action is given by a Schwarzian. The Schwarzian, I mean, this is the reduction of the action in this low energy regime. So this is something that comes from the exterior of the throat, which is the classical entropy. So all of the dynamics in this regime can be reduced to the action of this Schwarzian, which what it does is it's a measure. I mean, the Schwarzian is a function of reparametrizations between external time and throat time, in a sense. It's something that tells you how this throat is glued to the exterior at the mouth. And then this Schwarzian theory, as I described, it's a spherical mode. It's homogeneous. We're considering S waves. It's something that measures fluctuations in the height of the mouth. And then one nice thing about this theory is that it's simple enough that it can be quantized exactly. It has enough symmetry. There's a paper by Stanford and Witten where they argue that this theory can be exactly quantized using fairly sophisticated arguments, localization, that tells you that the results, even if you think that, well, I include one-loop corrections, well, one-loop corrections in this case are exact. It's the one-loop quantization gives you the full exact result in this case. So that was something that was done, I mean, a number of years ago for the pandemic by several people. Now, if you have this, one thing that you can do is to compute the gravitational partition function, the contributions to the gravitational partition function at small temperatures. You know that when you want to compute the gravitational partition function, then you have the semiclassical saddle point contribution. This is the semiclassical one, but then you also have to include, the determinant of one-loop fluctuations. Okay, this is the operator that gives you one-loop fluctuations. Now you analyze the different fluctuations. Many of them are suppressed at the very low temperatures that we have, or because they correspond to large sizes of the black hole. You can absorb them in other prefactors. What we're interested in here is in obtaining the factors that depend on the temperature. This can come from the quantum, the quantization of the Schwarzian action, this one determinant, and it turns out to a factor that is temperature independent. The result of that quantization gives you a factor that's T to the 3/2. So this comes from quantum fluctuation of the throat. And you see that these effects can be large. When the temperature, this temperature is smaller than this scale, then this factor is going to kill the partition function. It's going to suppress it strongly. Okay? So this effect can be large when the temperature is small enough. This is the semiclassical saddle point. This is the effect that I was saying, that quantum fluctuations make your saddle point not a narrow saddle point, but a very broad saddle point where the fluctuations are very large. So it's not a good, the saddle point approximation breaks down at the low enough temperatures. And this is the partition function. We can take the inverse Laplace transform, and from the partition function, we can go to the density of states. Instead of C of T, we go to rho of E.
Just to make sure that I understood this argument, I think usually the exponential is the leading term,
yes,
and the power law is the sub-leading correction.
Yes.
But
yes,
because of exactness, you
yes,
claim that it holds
yes,
even in the opposite regime when the power
yes,
law is dominant.
Yes, so the power law, so typical, well, first thing that you can say is that even if you cannot argue for one loop exactness, what you can see is that at least that there's a trend to go to lower energy states. That's what happens, for instance, in the case of the Kerr near-extremal black hole. For Kerr, you don't have this exact Schwarzian theory. You have a Schwarzian mode that you cannot argue. You don't have the same symmetry to argue that for one loop exactness. So everything that you can say is that quantum corrections are going to suppress or seem to be going to suppress. Now here you can argue more because you can say that, well, this is valid not just as a one loop correction, it's beyond this. So then this effect, we cannot really go to this regime of very small energies because there are other effects that one is neglecting over here, particularly that the density of states shouldn't be continuous. In the full quantum theory, it should be discrete, but this discreteness is something that we don't see over here. But to the extent that this is something that's a continuous density of states, this result that you obtain, this is the inverse Laplace transform of this quantity. When you do that, then you find that this is the exponential, but then this would be an exponential in the energy at very large energies, which gives you this. The since grows exponentially, but when E is small, then this is going to go like this, suppressed. Okay? And that's the way that we see the suppression. We're doing a counting of states, but we're not really doing a full microscopic count of states because this quantity, I'm still taking it from Gibbons and Hawking. This is not a full microscopic UV counting of states. I'm doing a path integral, the semiclassical gravitational path integral, improving over Gibbons and Hawking, including calculation of the one loop determinant in a regime that I can still have control over. There are also other contributions, quantum contributions, the log area. Those I'm ignoring.
So ST goes to 0. One does expect additional corrections which become important.
Here you're going to see, well, so from the point of view of the gravitational path integral, effects that become here are effects that are suppressed by exponential of minus the entropy. This may come from other topologies, because here I'm considering that the topology of the black hole remains the same. I mean, if you want in JT gravity, I'm doing a calculation using just the disk topology. I mean, it's the leading topology in then you can also have other contributions coming from other topologies and other things that you don't really have that much control over. You see that the gravitational path integral at the semiclassical level, you know that you're neglecting effects that are exponentially small in this S0. From the microscopic UV point of view, you know that the microscopic theory of the black hole states are going to be discrete. If the black hole is a good quantum mechanical system, that's something that you don't see at all here. So for energies which are exponentially small compared to, exponentially small to relative to in this range, and something that's e to the minus S0 times the energy times this energy scale, those scales you cannot resolve. What you see is that the density of states is going to a value that's, instead of being exponentially large, is at most order 1. You can't say anymore. So everything that I'm saying is with this caveat that I can't really go to extremality. The extremal object is a fully quantum object, and in order to describe it, the extremal ground state, I need the full ultraviolet quantum theory of gravity. Okay? And I'm doing here just gravitational path integral, which is an effective tool, very good, but limited. So that's the description of the state, of the black hole state. Now we're going to probe it with absorption. So I'm going to send a wave. I'm going to send a wave of a minimally coupled scalar field. This keeps my life simple, my calculation simple, into a near-extremal black hole. And then my near-extremal black hole is one where the parameters that I have are, well, this energy, the energy scale that tells me whether I'm in a quantum regime or not, and then the energy above extremality. These are the data that I need in my description of black hole states. There's this scale giving me the size of quantum effects, and then energy above extremality. I want to send a classical wave. that's conventional. I want to have a wave that has large occupation number, because I'm going to do quantum calculations, but still my wave, the wave that I'm probing is a semi-classical object. I want to have low frequencies, and I want to restrict to S waves. If you want, this is a bit like when people 100 years ago were doing calculations. You have a quantum atom, and then you scatter a classical wave and a classical electromagnetic wave, and then you saw how it was interacting with the quantum atom. Okay, I mean, you didn't need to do all of the quantum electrodynamics. You could still do this classical electromagnetic field probing the quantum hydrogen atom. Here I'm doing something similar. So we're taking this classical wave, it's propagating from infinity. There's going to be an in wave and an out wave, outcoming wave. Now, when this wave propagates from infinity to the mouth of the throat, here at the mouth of the throat, I can take it to be, this mouth of the throat is something that's an ADS2 geometry, so I can take the field here to be something that's going to be a time-dependent. Time-dependent, I mean, this is going to be an exponential, something that's going to be fluctuating. I can separate the radial dependence and the time dependence. So I can decompose here into two components, this wave, into something that's characterized by some weight that, for those of you who like ADS-CFT, this is the conformal weight of the operator that I'm applying at the mouth of the throat. Okay? So at the end of the day, what I'm having is that, so the quantum black hole is described by this Schwarzian theory. The Schwarzian lives here at the mouth of the throat. And at the mouth of the throat, I'm coupling this quantum mode that's describing fluctuations, I'm coupling it to the external field. And this is going to be this field, this wave that I'm having here, times some operator that corresponds to the response of the throat to external fluctuations. Maybe, I mean, I can put it also in the following terms. So what I have here is that my external field, this wave that I'm sending, is something that at the mouth of the throat is something that's oscillating, and then this is going to excite the black hole. I'm subjecting my black hole to some oscillating source. It's going to induce transitions between black hole states. I have this interaction between this operator that measures how the black hole is responding, and this is the external source that's making the black hole oscillate. So the black hole is being pushed back and forth by this external source, and then this is going to excite it, and induce transitions between black hole states. The black hole can absorb frequency of the external field, or it can emit, because of its stimulated emission, it can also emit quanta of this external field. Okay, so I'm going to have the two things. And then this is like any system that you're familiar with since kindergarten. Okay, you have some oscillator, and then it's a quantum oscillator, you're exciting it, and then it's responding by exciting or de-exciting. So how do we compute things? Well, again, kindergarten physics, Fermi rule. You compute what are the transition matrix elements between different energy states, and then you multiply by the density of final states. Okay, so this is something you can have. The final state can go to emission or to absorption. You can get, there's a prefactor here that you get from matching your field at infinity to the field at the throat. That's a semiclassical. The wave is propagating semiclassically from infinity down to the mouth of the throat. Then you have to compute some factor. The amplitude of the wave is going to be proportional to the number of quanta in the wave. And then we're considering that, this wave is semiclassical. In general, you're going to have three basic processes: absorption, stimulated emission, and spontaneous emission. Spontaneous emission, we're neglecting it because we're considering a wave with a very large occupation number. So everything is going to be proportional to the amplitude of the incoming wave. So again, you can have them, you compute, you have to consider the transition elements for emission or for absorption. So you absorb some energy or you emit some energy. This is a consequence of time reversal invariance. And then the total absorption rate per mode is something that, well, you take the absorption rate and you subtract the stimulated emission rate. Okay? Because what your total experiment is seeing is the total absorption. So you have to subtract what's being emitted by the black hole. Then you continue, well, doing conventional physics. You go from the absorption rate. This is something that is usually expressed in terms of, well, a gray body factor. The total number of quanta that are being absorbed, they are proportional to the number of quanta in the field, multiplied by the probability of absorbing this quanta per frequency. Then you apply what we call this the optical theorem, where you go from absorption probabilities to cross sections. So you find that the absorption cross section is proportional to the emission absorption rate minus emission rate. So at the end of the day, doing this is relatively conventional physics, nothing controversial. And then the final result is that the absorption cross section, when you include this, in particular, also this factor here that came from the propagation outside, then what you find is the absorption cross section takes this form, where this is all coming from the quantum black hole. There's a prefactor that turns out to be proportional to the area that comes from the matching coefficients. And then where do we get the transition rates between black hole states? Well, what we've been saying is that the quantum theory of the black hole for these modes, this is described by this Schwarzian theory. Schwarzian theory has different energy levels, so you can compute what is the density of states. We saw that, but when you can also compute essentially from the 2-point function, this is what's controlling transitions between two states. You can obtain also that the 2-point function or the transition rates between an initial state and a final state for an operator of the conformal dimension that I had there is given by this expression. So everything is very explicit. I can take these results now and plug them over here. And then I find this is the main result of my paper, of my analysis, that the quantum absorption cross-section, the near-extremal regime, is given by this function. Okay? This comes from emission, or from absorption, this will come from emission.
So, Roberto, quick question. So you're assuming here that the black hole is initially in an energy eigenstate, also that it's a pure state?
Yes,
I mean,
yes,
but the results generalize also to more general cases?
So I'm considering that I'm doing, if you want, a calculation that's in a microcanonical ensemble. I'm fixing the energy, I'm fixing the spin. I could consider that the black hole is in some other, in an ensemble of states. That can be done. Some cases, some other people have done similar calculations for black holes in a canonical ensemble, in a thermal state. This can be done, yes. I mean, it follows with relatively simple modifications. What I'm describing here is just this case where I'm fixing the energy. I'm also fixing the spin and the charge. Fixing the spin of the charge, that's because I'm doing S-wave neutral scattering. But one could also consider other things. And we've done some calculations considering other cases as well. So it's possible to do that, yes. So the result is this. And of course, the first thing that I did is, well, a sanity check. When the black hole, I mean, this is the full result, when the black hole is with an energy much larger than this energy in the quantum regime, I should recover the universal result that the black hole cross-section goes to the area. And that's something that follows from this result. So it's a straightforward check. But then, of course, this is just a check. I want to know what happens when I'm in the fully quantum regime. And then the best thing to do, or simplest thing to do, is to plot the results. I'm plotting here the absorption cross-section relative to the area, the ratio between the cross-section and the classical area. And then these are plots as I go. Well, this is a semi-classical result. They are equal. But then, and this is what I cover also, when the energy above extremality is much larger than this energy scale, then these curves go over to this value. But as the energy above extremality gets smaller and smaller, then I get larger and larger deviations away from the semi-classical result. And this is what I found. And then I said, well, what's going on here? I should spend more time analyzing this. Okay, you find this. There's a kink here, and the kink is essentially because when at this energy, you cannot have a stimulated emission because you can, if you emitted a quantum with more energy that's available, then what you would be violating the extremality bound. And that's something that well, you're not allowed to do. Okay, that's the reason that this kink appears. There's nothing more mysterious about it. So then, well, as I said, well, since we have that the density of states is less than what the semiclassical area would give you, then what we've seen, and nevertheless the absorption cross-section is larger than the semiclassical result for the area. So then what this is saying is that if you just went with the density of states to estimate the absorption cross-section, then you say, well, the density of states is underestimating the total absorption. So what's dominating the absorption is not the density of states, it's the matrix elements, the transition elements. So this is what I did then to, I want to plot what I get. So I plotted, so here's the plot of final states, density of final states, and this is the transition elements between initial and final states for absorption. So you see that the quantum transitions are larger than semiclassical transitions for absorption. There are fewer states, okay? So there are fewer states for absorbing. But when you multiply them together, then what you find is that the quantum effects still win over the semiclassical effects. So this enhancement of the absorption transitions, individual absorption transitions, overcompensates for the fact that there are fewer states available for transitions. So that's the main effect, telling you that the quantum effects should be are larger. Then there's this other effect that stimulated emission is suppressed. You see that the stimulated emission, when you plot the number of final states, then you see that this is very heavily suppressed. There's nothing above here because, well, when you have less than zero energy above externality, there are zero states. So this effect, the stimulated emission, is suppressed because you have many fewer final states. Now that's the result, and this is so. I mean, these plots, and this is the explanation of the results that I told you at the beginning of the talk. Now this, I don't know if you have any questions. I'm now going to kind of summarize a little bit and go to the final part. But if you have any questions at this point.
If you stop for questions, I will ask one.
Sure.
I want to understand, to make sure that I understand the general strategy for computing the cross-section. So I believe you're not computing it in the geometry, but rather you're using some quantum information, in particular the density of states, which is known from the Schwarzian model.
Yes.
And you need also the matrix elements. The matrix elements you get from the geometry or from elsewhere?
From the Schwarzian. They're again from the Schwarzian. So what I'm doing, if you want, what I'm doing is I have this black hole which has an asymptotically flat region outside the throat. And then what I'm doing is the throat, I'm fully replacing it with the Schwarzian theory. So I don't have the I'm not looking anymore at the semiclassical geometry in the throat.
So now it's a quantum model.
Yes.
You're replacing the black hole by a specific quantum model, and
exactly.
you perform the scattering within this model.
Yes.
Okay.
So all of the black hole, I'm not looking anymore at the interior of the throat. All of this is my quantum Schwarzian theory. And then I'm coupling my quantum Schwarzian theory to the external field, to the external wave.
Good.
Okay.
Thanks.
So that's essentially what we're doing in this work and other things that we're doing. Everything that you did formerly by having, because the way that we usually work this in a semiclassical approach is, well, you do this match asymptotic expansion where you have the far region and then you have the throat region and then you match them. But then you were matching to the far region, you were matching a semiclassical throat region that you still treated. So now I'm saying, no, I throw away this semiclassical geometry for the throat and I'm replacing it completely with this quantum model, with this quantum mechanical theory. So that's what we've been doing. Well, one thing that follows is that the result is also very general, very universal, because this Schwarzian theory is very universal also. I mean, whenever you have these ADS2 throats, or almost whenever, in a very large number of cases, the only thing that you have to change, the Schwarzian theory depends on a few parameters on this energy scale, the energy above extremality, and, well, the overall area of the black hole, of the mouth of the throat. So if I want to do this for other near-extremal black holes, as long as they are not BPS or not near BPS, they are not supersymmetric, because in that case the Schwarzian theory would change. But in general, that's a very general result under some relatively mild assumptions. Then I can compute the absorption cross-section for other black holes, Rayleigh Nostrum in other dimensions, or you give me other theory, Einstein-Hilbert gravity theory, that also has a black hole close to extremality, then I get the results just by changing the explicit values from these parameters. So this is valid, as I say, for static near-extremal black holes in theories of Einstein-Hilbert gravity, because this gives you the Schwarzian. In other cases, you may also get a Schwarzian, but and then you can also couple it to matter, as long as it's not supersymmetric. The reason that supersymmetry changes this is because then when you have supersymmetry, then you also have other very light modes, fermionic modes, besides the Schwarzian. And this can change the result by a lot, because you have these additional contributions and we can change things significantly. Other things that one can do, well, I've described absorption of spinless waves. So that was the S wave of a scalar field. We can also consider higher partial waves. We can also consider photons and gravitons. And these are things that my student Stefano Trecci is doing. The preliminary results is that the partial waves seems to be, and the absorption cross-section seems to be lower, the quantum value lower than the classical value. But I'm not saying more because we still have to analyze the results. So that's very recent. We have the results and we have to still deconstruct them. Another thing that one can do, and we're talking about this, another way of probing the black hole is by, instead of sending a wave, you introduce some tidal deformation. And then this tidal deformation is going to deform your throat, but now your throat is not a classical throat, it's not a semiclassical throat, it's a quantum throat. How does it respond? So what is, and the deformation is measured by log numbers, so what is quantum log? And that's something that we're also working on. We don't have the results yet, but well, maybe we can talk about this a little later. So my conclusion, the conclusion of my talk, coming now to the end because I'm running over time, is that I began this talk by asking whether we can observe large quantum fluctuations of the geometry of spacetime. I think that the conclusion of the study that I've told you about is that the answer is yes. That we can perform these classical experiments that can probe the quantum regime of near-extremal black holes, and then we can extract experimental prediction, and that if you perform this scattering experiment of your near-extremal black hole and then you measure the cross-section, if the result that you get is larger than the classical value, then maybe you can then claim that the object that is down there, that black hole down there, is a quantum object that's undergoing large quantum fluctuations, and these large quantum fluctuations are enhancing the cross-section. And with this, I'll stop and thank you for your attention and for your questions. Thank you.
Thank you, Roberto, for the interesting talk. Any additional questions?
Do you have any idea how to arrange to send S wave to the very massive black hole which is somewhere in the universe?
And so, now it comes maybe the moment for disappointment about possibilities of observing this. This quantum regime of black holes is a regime that's really very close to extremality. You just have to imagine that if you throw a photon into this black hole, then the photon is going to, just a single photon is going to make the black hole spin, is going to raise the energy, and then this is the energy scale of the quantum fluctuations. The energy of a single photon being absorbed by the black hole. If that isn't a tiny energy, then so it's something that I don't think that there's any realistic. I don't know whether maybe at least in conventional theories of gravity and black holes, I don't think that this is something that can be observed.
Is that a single photon at the characteristic wavelength scale of the black hole itself?
Yes, yes.
Okay.
Even at low frequencies, the absorption of the photon. So a single photon, because a single photon, that's also something that I like about this is that the level of control that we have over these black holes. Because we can see the quantization of a spin in the black hole. We can control that. We can distinguish in this theory between a black hole that's spin exactly 0 or spin 1 or 1/2. These are things that can be described within this. So spin in this regime is not a semiclassical continuous variable. It's a quantum regime. So then this means that you're really very close to 0 temperature. It's something that you have this is a quantum object, but it's a quantum object that's extremely fragile. Extremely fragile, and I don't think that there's any chance of forming this, certainly in astrophysical settings. Whether, I don't know, or the conventional astrophysical settings, whether there's some modified theory of gravity, maybe you can enhance the effects or other things, maybe something can happen. But for prospects for observation in our in this universe, in this with these technologies and with these resources, maybe some future civilization, advanced civilization can control this, but it's a very long-term prospect. That's why I was emphasizing that I'm doing thought experiments at all moments. It's disappointing, but I still find that the fact that we can have control over quantum fluctuations of the geometry, this is quantum gravity. These are large quantum fluctuations of the geometry. It's quantum gravity. There's no string theory. There's no holography. For people who hate strings, people who say they should still buy this, because what I've described are semiclassical path interval. That's what I was using.
Question: can you express the regime in which we don't trust the classical near-extremal picture, but we must incorporate quantum corrections, this regime that you studied, in terms of the specific heat, the m by dt
I imagine that
of the black hole being maybe smaller than 1 or something like that.
I mean, I don't know. I mean, it's going to be I prefer to work in the microcanonical ensemble rather than the temperatures, because here we're in a regime where you don't have ensemble equivalence because you have large fluctuations. That's one thing. Then speaking about the specific heat, I think it's possible. I think it's going to be an extremely small specific heat. It's something that's exponentially small in the semiclassical entropy, the specific heat, near this regime where things fail to be.
What I'm having in mind is that the specific heat could succinctly express the idea that you mentioned, that a single quantum cannot take more energy than the energy above extremality.
That's true. Okay, yeah. So the quantum regime, I think it can be characterized in those terms. Yeah, because I think it's fairly easy. I won't attempt to do it live, because I'm very good at humiliating myself when trying to do calculations without preparing it. So you have to take two derivatives, or a derivative of this, and then I think that this energy scale is going to correspond to the scale of the specific heat.
You see, the E by dt would be proportional to T over EB, and this is roughly the small parameter that you were discussing.
Yeah.
So maybe the E by dt, which is the specific heat, would be a nice way to express this idea, whether T is larger or smaller than EB.
Very good. You're saying it because whether the specific heat is larger or smaller than 1. Yeah, exactly what you were saying. Yeah, when the specific heat is smaller than 1, then that's the regime where this semiclassical thermodynamic breaks down. Yes, good. Okay. Very good. Yeah, I think that's a neat way of putting it.
Thanks.
I have a question also. So you were mentioning that some things need to be revised. What we know about near-extremal black holes,
Yes.
the love numbers, for example. So also quasi-normal modes come to mind. Also in that context, I mean, if you're thinking about a larger cross section for absorption, then would you expect larger imaginary part for the quasi-normal mode? Because it's known that they have a vanishing imaginary part in the extremal limit. So do you expect some?
So that's something I think it would be interesting to study. And I think it's possible, very well possible. I mean, because again, quasi-normal modes, the information about them, that's contained in the two-point function. It's essentially, I mean, it's coming from the same information, all of this. So the one reason that I thought that maybe quasi-normal modes don't tell you much about it is that quasi-normal modes are dynamical modes, and they are kind of, I think that they are mostly localized outside the throat, or from the mouth of the throat to the outside. They are not inside the throat, because the ADS2 throat, no, it's not true.
No, not the ones that decay very slowly. The ones that decay very slowly are actually localized mostly in the throat, I think.
Or ADS2, because the thing is that ADS2 doesn't have dynamics. I mean, local dynamics. So then that's why I don't think, I mean, if it's ADS3 or higher, then you can have modes that are that propagate inside the throat. You can have propagation in ADS4, ADS5. I mean, that's very well known. These are the long-lived hydrodynamic modes. But ADS2 doesn't have these modes because it doesn't have, I mean, the dilaton gravity doesn't have propagating degrees of freedom. So that's why I would think that quasi-normal modes are probably less. But nevertheless, I mean, they can be localized near the mouth of the throat, and there they can interact with the Schwarzian. And then there may be something that I think the information to do it is, again, in the two-point function. And I think the calculation should be
Well, you can even think about the quasi-normal mode of a scalar, for example. There you don't have that argument of no dynamics. But,
it's a calculation that, I mean, if we haven't looked into it in more detail, it's because we've been doing other things. But it's something that, I mean, my first reaction is, well, something that I'm telling you about now. But it's something that it's worth looking into in a little more detail and see what you get. Yeah, because I think it's, I mean, the information, as I say, it's already there. I mean, you just have to find a way to extract it. It's a two-point function of the stress energy tensor. That's what the quasi-normal modes are. And the poles in the ones yeah. So that's doable. Also, well, you know about other phenomena near extremality or at extremality that like Aretatis instability. And that's something that's still, I mean, I've been discussing it with some people, and it's not very clear what to do about it and how it enters in this game. Yeah, and then, well, your work in particular, I think it's very relevant here because you and Harvey, you are the ones who studied what happens when you're also moving away from extremality, which I think is a physical question to ask. So yeah, one of the things that I mean, you know, to study this, one of the things that I want to do is go back and read your paper on this more carefully. Yeah.
Okay, any other questions? If not, let's thank Roberto again.
Thank you.